Welcome to another VEXcode VR tutorial. In this session we're going to be looking at the sensors on the robot. So a robot having sensors on it is a vital part of the way it operates, and it allows it to interact with its environment, sense things like walls or light levels or sound levels, or all sorts of things that you would need on a physical robot for it to interact with its environment. And on our virtual robot in VEXcode VR we also have sensors that we can get data from. So the first thing I want to do is just open the playground. Let's take a look at the 3D view so we can see the robot, and let's have a quick look at the sensors that we've got on it. It's probably also a good idea for us to flick to the sensing part of the toolbox so that we can have a look down the list of sensors as well. So the robot has got a number of different sensors on it. It's got bumper switches here on the front on either side, so that can detect a collision with the wall on either the left or right hand side. So there are bumper sensors. We have a distance sensor on the front here that's measuring distance to an object in front of the robot, and that is also what we call the front eye as well. So that can be used for colour detection and a few other things. We'll look at that later. On the bottom we have a down eye, so that is very similar to this sensor here, but looking downwards, so it can detect colour underneath the robot. And then integrated within the robot, things that we can't physically see on it, we've got encoders on the motors, so they can tell us how far the robot has travelled, and then we have a gyro inside, so that can tell us how far the robot has rotated in one direction or the other, and we have a timer as well. So the sort of the virtual microcontroller inside the robot has a timer built into it so that we can time the amount of time that's elapsed between various points of the program. The other thing that's really important to know is that this little button over here brings up a panel called the monitor. And the monitor is a way of us monitoring the sensor data or things like variables and lists that are stored in the virtual microcontroller of the robot. So it allows us to see that data and get some debugging data from the robot as well. So the monitor function here, this little like speedometer icon, this is something that you're going to find really, really important when you start playing around with the sensors. The other thing in the monitor is we have a little console display here that we can print data to as well. So it's kind of like the LCD display on a VEXiQ brain or on a V5 brain, and it just allows you to print data to the screen as well. Right, let's get started with looking at the sensors. So let's start with the timer, because it's just a quick one to have a look at. And so the timer on the brain is running all the time. From the moment you start running a program, the timer starts running. The options we have here are to reset the timer. So this is just a block that sets that timer back to 0 whenever this block is executed. And then we also have the timer in seconds block here that allows us to, it's basically a numerical value that we can then bring into our program to manipulate in various ways, store it in a variable or something like that. So just to show you that in action, what I'm going to do is create a really simple little program, and I'm going to start with a wait for 5 seconds just so we can see some time elapsing at the beginning. Then I'm going to reset the timer so that we see it go back to 0. And let's say I'm going to use this for some kind of practical application. So let me say I want to know how long it takes the robot to travel to, let's say, 600 millimeters. So after I've reset the timer, what I'm going to do is drive forward 600 millimeters. And then after that, I want to capture the current timer value in a variable so that I can say, well, after 600 millimeters, this is what the timer value was. So I'm going to create a variable. So I go to variables, make a variable, and I'm going to call it total time. And at this point here, I'm going to set the total time variable that I created to the current time in seconds. And so at that point I've stored it. So the fact that the timer is still running is irrelevant. I've stored a snapshot of it at that point, which I can then see in the monitor. Now, the way I see these things in the monitor is by using the little checkbox that's just to the left. So I want to see the timer in seconds, and when I tick that, you'll see that timer in seconds has now appeared over here in sensors. And if I go to variables as well, because I want to see this total time variable, I can tick next to total time, and that now appears in my variables as well. So let's just to give this a bit more of a practical purpose, we'll say initially we're going to have the velocity, the drive velocity at 50%, and we're going to time how long it takes for the robot to travel 600 millimeters at 50% power. Now the reason I put this pause in here is just so you can see that the timer starts running straight away at the start. So when I run this program, the timer is now running for 5 seconds, and after 5 seconds the timer will reset to 0 and drive forwards. And after the 600 millimeters, this is the time that I captured. So it took 2.416 seconds to travel 600 millimeters. And you can see the timer is still running, which is why I needed to capture. We don't have a way to stop the timer, it's always running. So we needed to capture it in a variable there. So if I reset now, so 2.416 was what it took at 50% speed. If I change this to 100% speed, now how long does it take to travel 600 millimeters? So we've still got that 5 second wait at the start. 5 seconds will elapse and then we'll start. And now 1.229 seconds at 100% speed. So it makes sense that it was roughly kind of half the time because we were going twice as fast. So you can use that to do things like calculate how fast your robot travels, but you can also do all sorts of other things with the timer where you need to know how long a particular action has been undertaken for. So that's the timer. Let's reset the robot, untick that. Then we've got drivetrain sensing. So there's two here at the top that are booleans. We know they're booleans because they're these six-sided shapes. So that means they return a true or a false. And we've got is drive done or is drive moving. So they're kind of like the inverse of one another. If is drive done means has it finished doing the last drive instruction that we told it to do. So that could be travel forward for X amount or turn right for so many degrees. Is it done? We'll get a true back from that when it's complete. And is drive moving? Kind of like the opposite. If the drive is moving, then it's true. If the drive is not moving, it's false. So if I just check the little boxes next to those, you can see that they start off as opposites to one another. And let's just see sort of a practical, see that in action. If I say drive forward for 1500 at 50% speed, you'll see when the program is running, when the robot is moving, is drive done will become false because it's moving, it's not done yet, until it's finished and got to its destination, i.e. 1500 millimeters, and then these will flick back. So if I run that now, you can see those change to the opposite state, and then when we get to 1500, change back again. So it's just a boolean that says is it moving or has it completed the drive move. We also have some numerical values there, so drive heading in degrees and drive rotation in degrees. If you look back on my drivetrain video that I've already done, I explain the difference between heading and rotation. So just to very quickly recap on that, heading is like a compass heading. So 0 degrees is straight up the field, 90 degrees to the right, 180 degrees behind, 270 degrees to the left, and then back to sort of 359. And then if we keep turning right, it'll go back to 0 again. The rotation in degrees is a cumulative value. So let's imagine again that I turn fully through 360 degrees and then again, then the rotation in degrees would go past 360 and be cumulative, so get to 720 and so on. Let's see that in action. What I'm going to do to show you that is try and integrate both. So what I'm going to do is just make the robot turn right. And this, I'm just using the turn right command, not the turn right for X amount of degrees. So we're just telling it to keep going until something else happens. And in this case, I'm going to say, wait until the rotation value is greater than 720. And so from my sensing, I'm going to get the drive rotation in degrees rather than the heading. And we'll show both in the monitor so we can see what's going on. So there they are. They're both 0 at the moment because the robot's facing straight forwards. And once it's turned through 720 degrees, I then need to tell it to stop. And when this is running, what I'm interested in is looking at these two values here and how they ever so slightly differ. In fact, what I'm going to do is I'm going to turn my turn velocity down to maybe 25% so we have a bit more time to see that happening. Turn the robot nice and slowly. So as I play here, so the robot's now turning right, and you can see that the drive rotation in degrees and drive heading in degrees are increasing at the same rate. But as I go past the first turn, heading goes back to 0. Rotation is cumulative, so it's still adding until we get to just past 700. So I said greater than 720, so there's a little bit of overshoot there. Got to 722 degrees, so that's 2 complete rotations, and the heading is just past 0 because, of course, that's our compass north. So that's basically getting gyro data there, heading in degrees and rotation in degrees. Let's uncheck those. Next we've got bumper sensing. Again, we can tell by this sort of 6-sided hexagonal shape that it's a Boolean, and that can be either using this drop down, the left bumper or the right bumper. And if we go back to the 3-dimensional view, so the robot has this bumper switch on the left hand side and a bumper switch on the right hand side, so we can use those. Great for like maze solving and those kind of things. Have we bumped into something? Which side was the object that we bumped into? Let's create a simple program for that. What I'm going to do is have a forever loop, so we just are bouncing around the field all the time, and I'm going to have one block here just to tell the robot to drive forward. Again, not for any specific amount, just always driving forward. And then I'm going to have 2 if statements to check the left and the right bumper status. So I'm going to sensing now, and I've got left bumper, and here I'll have right bumper. And what I want to do is just basically, if I bump into something, in the case of the grid map field that I'm on right now, that's going to be if I bump into the wall, then I want to reverse away from it, turn and carry on. So if I bump into something on the left hand side, I want to assume that I've bumped into a wall to the left of the robot, and so I probably need to turn right. So what I'll do is, for the left hand bumper, I'll reverse up ever so slightly, probably only needs to be 150 millimeters, and then I'm going to turn right slightly, and let's say we'll turn right for 55 degrees. So we're turning away from the thing that we've bumped into on the left hand side, and then I'll duplicate those blocks and put them in for the right hand side. But instead of turning right, if I bumped into something on the right hand side here, I probably want to turn left to turn away from it, like this. And then finally what I'll do is go back into my sensing toolbox, and I'm going to tick the little button here, and you can see that brings in to the sensors panel of the monitor the current status of my left and right bumper. Some of these things actually are the same as what you see in this data here. So we have bumpers here, and you can see they're also that data is also shown there. You can kind of switch this off to give you a bit more space on the playground to see what you're doing. Especially useful on the top-down view when you can see a slightly bigger version of the playground, and then you can use the monitor there to see that data instead. So let's keep our eye on those as the robot drives around. So currently they're false, and so none of these if statements are true, and therefore it just continues to drive forwards. As we bump into the wall, they will go true. It actually happens, so you can very quickly see the left bumper there flick to true, and now this left bumper is going to be the first thing to collide, so keep your eye on left bumper pressed, and there it goes true ever so quickly. And so we're just getting that Boolean data, that's triggering the if statement here, and then we're turning away from it. So that's kind of like a simple bump and avoid project using the left and right bumper sensors. Okay, let's reset and move on to the next sensor. So we've done bumpers. Now we've got the distance sensor. So we have the distance sensor on the front of the robot, if you recall. So that's kind of here physically on the robot and looking straight ahead. And what that's doing is detecting the distance to an object in front of it. So let's click on this. Again, it's displayed here. I'm going to switch that panel off just so we've got a bit more space. And I'm going to use the monitor to show all of my information. So firstly, we have the Boolean here has distance found an object. All that means is something, anything at all in front of the robot. Doesn't matter how far away it is. Well, actually, it kind of does. The threshold there is 3,000 millimeters. So basically, if it's less than 3,000 millimeters, it thinks it's seen an object. So if I turn both these on and see them in the monitor, you can see here in this field it is impossible because of the length of the field, which is 2,000 millimeters in total. It's always going to see the wall. It's impossible for this not to be true on this playground, but on some of the other playgrounds, I'll show you in a sec, it is possible for that not to be true. But we've got the distance in millimeters, so we're 1,845 millimeters away from this end wall. So let's use that in a program. I'm going to say drive forwards, and then I want to stop. Let's say I want to stop 500 millimeters from the edge of the field. So I'm going to say wait until I'm less than 500 millimeters. And the thing I want to be comparing is from sensors is the distance in millimeters. So wait until the distance in millimeters is less than 500 and then stop the robot driving. So let's use the top-down view. You can see it heading towards. So these squares are roughly 200. Well, these squares are 200 millimeters each. So that's 2, 4. So we should be stopping somewhere in the middle of this square for 500 millimeters. And you can see as I start the program, this is reducing because we're getting closer and closer to the wall. That's the distance to the wall reducing. And when we get less than 500, we stop. A little bit of inertia to take us past. So we've gone to 490. And you can think of ways to deal with that. So that overshoot there, how can we deal with the overshoot? Well, for example, we could slow down when we're getting nearer. So let's use repeat until here, slightly different logic. So two things, we'll say we want to get less than, rather than less than 500, let's go less than 501 millimeters. So we've got 1 millimeter of overshoot kind of built in there. We don't want to use equal to because it might be that equal to happens for such a short period of time that we don't want the program to skip past that. So less than means if we've overshot, then it's still going to stop. Equal to means it would only stop on exactly 500. And so we don't want to do that. We want to say less than. Again, I want the distance in millimeters there. And I'm going to add in an if and else here using this same criteria. But I'm going to change this ever so slightly to be, I want to do the last 150 millimeters very slowly, or probably even only the last 100 millimeters would do. But let's say, so I want more distance on that. So 650. And let's change the drive speed. So we'll do 50%, or if we're getting very close to the edge, then we'll slow right down to 10%. So what this is going to do is drive forwards, and it will drive forwards until we get to 500 millimeters, so less than 501 millimeters from the wall. And we've got another if statement that's being repeated here. So if the distance is less than 650, so we're getting into this last little section here, then it will slow right down to 10%. But whilst we're in this first part, any other circumstance will be going at 50% speed. So let's run that. And you can see, again, this value decreasing. And as we get to the last 650, the robot slows down. And so now we're very close to that 500 millimeter. We've only overshot by 1 millimeter now because we've dealt with that by slowing down ever so slightly, so much less overshoot. So that's the distance sensor. If I quickly flick to the so some of the playgrounds don't have a wall all the way around the edge, and one of those is the Castle Crasher. So the Castle Crasher here, if I go to the 3D view, you can see there's no wall around the edge. We have a red line around the edge, but there's no wall. So that allows us to basically drop off the edge of the world. And at the moment, my distance sensor is seeing 557 millimeters to an object. That's this castle in front. Now, if I just turn right for 45 degrees, so I'm looking through this gap here, you can now see, so the distance is 3,000 millimeters. Well, that's actually, it's greater than 3,000. It's the 3,000 is the maximum that the distance sensor will see. So anything 3,000 above means basically it can't see an object. That's the infinite distance off the edge of the field there. And you can see that distance found an object has gone to false because now there is nothing in front of it at all. So if I do another very simple program, let's say I want to set my turn velocity to 10%, so we're going round nice and slow, and we'll just turn right continually. So we see what happens now. As it goes past this object here, it comes true, and then back to false again. The next object we're going to see is this one here. It's currently false because we're looking into space, but this will go true again as we flick past that one, and again as we come past the big castle, back to true because we've found an object. So we've got a Boolean there, and then the actual distance numerical value there. Right, back to the sensors. What else have we got? So we have the front eye. So front eye near an object, that's very similar to distance sensor found an object. It's a certain distance, physical distance from an object. This is the one I'm going to focus on. So the colour that it's detected. And we have two eyes on the robot, the front eye and the down eye. They both do pretty much exactly the same thing. I'll use the down eye because we're on the field that has this nice red perimeter, which is a cool thing to be able to detect and stop us falling off the edge of the world. So let's start by just saying, just to show what happens if we don't try and detect that line. If I drive forwards, then I can fall off the side of the playground, and then that's the robot just falls down and down. So I need to detect that red line. So let's say we'll have a forever loop, and what I'm looking for is the red line. So we'll have an if and else here, and we'll say if the down eye is detecting red, so it can detect either red, green, blue, or nothing at all. If the down eye is detecting red, so that means it's got to this line around the edge at some point, then we want to reverse up a bit. So let's say reverse up for so 300 millimeters, and then we're going to turn. So we'll make it let's make it very similar to what we had in the bump and turn, so something like a 55-degree turn. Otherwise, we just want the robot to drive straight forwards. So if it's not detecting the edge, just drive forward. We're going to try and crash some of these pieces of castle off the edge. And so it's just going to drive around aimlessly, but if it gets to the red line, bump and turn. So off we go, crashing through these first few bits of castle. And what we're looking for, there we go, we see we turn there. What I haven't done is turned on the down eye in the monitor. So here we are, we're looking at it. Has the down eye detected red? There, flicks to true every time this robot gets close. Here we go, watch this here, true, and therefore triggers this part of the if-else statement, reverses up and turns. So that's stopping us falling off the edge of the world. What this program isn't doing is actually looking for any objects at any point, and therefore making any useful move towards another object, so that's something you can build into the program, but that's how you can use the down eye to detect a colour on the ground. So it's the same for the front eye as well. So that's the front and the down, you're getting the same data from each. And then the last thing I want to look at is the location sensing. So this one's really handy for driving to a specific point on the field. So let's say, go back to the grid map. So looking at this, the starting position. So the field itself is 2 meters by 2 meters, or 2,000 millimeters by 2,000 millimeters, and this central point is grid reference 0. Right in the middle is 0, 0. I'm currently at minus 900, minus 900, so I'm minus 900 on my y-axis, so the middle of this square basically, and I'm minus 900 on my x-axis, the middle of this square. So as I said, this middle point is 0. I can get data from my x and y axes using the location sensing. So if I wanted to drive, say, back to 0, let's show those in here. I mean, we've got them in here anyway, but I'm going to switch those off so we've got a bit more space on the playground and just look at them here. So you can see the starting position, minus 900, minus 900. I just had to run the program there just to get those to set themselves to the starting position. And now what I'm going to do is I'm first going to drive forwards to the 0 position. So let's say we will start by driving forwards, and we're going to repeat that until, and I want to get as close to 0 as possible. So actually I'm going to do this similar to how we did the distance sensor. So let's say I'm going to use my repeat until, and I want my, so it's X is a left to right, Y is up, so we're going to drive up first. So I want to say repeat until my Y axis is greater than, and we want to try and get to 0, so greater than minus 1. And let's slow down a little bit as we get close. So we'll say if, we'll use an if and an else just to keep it tidy. So if the y-axis is greater than, we'll do the last 100 millimeters slowly. So if it's greater than minus 100, we will slow down. So let's go right down to 10%. Otherwise, 50%. So then when we get there, we want to turn right 90 degrees so that we're facing into the center of the field. And then we're going to do something very similar. I'm going to duplicate this code here. But this time, rather than the y-axis, we're going to be looking at the x-axis data. And again, we're starting in this minus because this is 0 here. This is minus numbers. This is positive numbers going past 0 here. So I can use exactly the same logic. And then at the end, we want to make sure that the robot is stopped. Right, so let's see that in action. So we're now driving forwards, and this is getting down closer to minus 100, and the last bit will be done nice and slowly. Then we turn right, and then we're heading... Oh, I never told it to drive forward again. So now we're stuck in this loop because I never told it to drive forwards. So at this point here, I need to say, hey, you've got to drive forwards again. Let's reset that, give it another go. So driving towards minus 100, at which point we'll slow down, do the last 100, and then the same again to this point. And that gets us pretty close to 0, 0. You can have a play around with the programs to try and get your yourself into really accurate positions. But this is a really useful tool. Being able to sense your XY position is a really useful tool for playgrounds like the disk transport, where you might want to tell your program the exact location of all of the disks that you need to go and collect. And so then you can make your code more efficient by maybe storing the coordinates of those in lists, so these XY coordinates in lists, and then you can write code to drive to those coordinates. So that's a brief overview of the sensors. I hope it's useful, and we'll be back with another video to look at variables next time.